hear you.
Okay, yeah. So yeah, good morning everyone.
Yours.
Yeah. So good morning everyone. My name is Sagar Kulkarni. I am ESR 5 and the probably the last speaker in today's session. And I'll be discussing about our recent work on quantifying the uncertainty in the flame impulse response model, which is estimated from LES with uncertain thermal boundary condition. So this work has been submitted to the ASME Turbo Expo 2021, and we are awaiting for the final reviews, which are due this week. So let's jump right into the topic. By now, most of you know that thermoacoustic instabilities are quite prevalent in low emission gas turbine combustors. And therefore, there is a need to design them for the prediction of these instabilities, for the better prediction and for better performance of the engines. So generally in the thermoacoustics literature, we find many people using a hybrid approach to determine the thermoacoustic stability of a system. In this kind of approach, where we have on the first, we do an acoustic model of the system, wherein we deal with the scattering and propagation of the acoustic waves in the system without any flame element. And then we determine the flame model, which is exactly the influence of these acoustic waves on the flame. So typically the flame model can either be obtained from experiments or from numerical experiments, such as doing harmonic excitations, as many have showed you, and also doing a broadband excitation and applying system identification technique to determine the flame response in the desired frequency of interest, which I will be talking about in my future slides. And so once we have identified the acoustics and the flame, then we use them in conjunction to solve the eigenvalue problem to determine the stability characteristics of the system, which is just an illustration shown here. So as you can see, flame model plays a very key role in the determination of the whole stability analysis of the system, and we are going to concentrate on this for now. So, most of them have already in the literature, they have shown that the flame response which is obtained is uncertain due to the lack of the knowledge on the incoming flow conditions, such as the inlet velocity here, or also the various thermal boundary conditions which are shown here. So most oftentimes these kind of boundary conditions are difficult to measure in the experiments, and then they remain uncertain. Now, we don't have exact knowledge about these boundary conditions. So this kind of uncertainties where we have lack of knowledge on the system parameters can be termed as epistemic uncertainties. And therefore, when we are trying to determine the flame response, so indeed this, either if you determine it experimentally or numerically, indeed will have some kind of uncertainties in the determined flame model. So therefore, there is a need to quantify these uncertainties for an accurate stability analysis. And as I said, studies have already shown in the past that the flame is sensitive to the change in the boundary conditions. For example, Duchesne in their study showed that if they when they changed the inlet duct wall temperature, when they specifically when they increased it, the flame speed is increased because of the hotter premixture which is being fed to the flame, and then this decreases the flame length, and thereby the flame delay is decreased. So that means the flame is sensitive to these boundary conditions, and this kind of uncertainty has to be taken into account for when you determine your transfer functions. Similarly, Mahia in their study also showed that the effect of the boundary effect of the bluff body temperature on the flame attachment and as well as the flame dynamic response. So they showed that if you have when you have a uncooled bluff body, so that means the bluff body temperature is close to 700 Kelvin. The flame, you can see, attaches close to the bluff body because of the hotter premixture which is being fed to the flame, and then because of this, the flame length is shortened, as you already saw. I explained in this case, and you can see on the right that the flame delay is not so steep as compared to the cooled bluff body case, which is having a different boundary condition. So therefore, an accurate indeed, you cannot have an accurate estimate of the boundary conditions which are coming from the experiment. So you need to account for these uncertainties when you determine your flame model. So as I said, okay. Earlier that I will be using the flame model, which is obtained from LES SI approach, as we call it. So in this kind of approach, where you excite the flame with a broadband signal with certain characteristics, which elicits only a linear flame response, and then we record the time series of the fluctuations, of the velocity fluctuations, which are fed to the system, and then we also record the global heat release rate from the system. And then we apply the system identification technique, which is a form of supervised machine learning, because you try to optimize for the parameters. And then we obtain the flame impulse response. So here the flame impulse response, which is shown in the time domain, is a distributed time delay model, wherein each delay corresponds to these FIR coefficients here. So however, when you apply the when you apply the system identification techniques on a turbulent flame, so which has which is riddled with the combustion noise. So then your data, which is shown here, is corrupted by the noise, and then this kind of noise results in an uncertain flame response, as shown here from this dashed confidence intervals. So this kind of an uncertainty can be called as aleatoric uncertainty. That is because even by increasing the knowledge of the system, like say if we know exactly all the boundary conditions, but still we cannot decrease the uncertainty because of the noise which is there. So this kind of uncertainties are called as aleatoric uncertainties, which are also there in the system when you determine your flame impulse response from LES-SI. So in summary, when you try to determine the flame response, say from LES-SI approach, you have two kinds of uncertainties coming into your flame impulse response model. So one that is coming from the lack of knowledge of the boundary conditions, and the other one is applying your system identification technique on a flame which has noise. So this results in an uncertain flame response, and which then used with the suitable acoustic solver gives you an uncertain stability prediction. So maybe a marginal mode here can which is rendered stable, and because of the uncertainty, this can be also unstable, and this needs to be properly accounted for. So what has been done previously in the literature then on this uncertainty quantification? So Guo et al. They studied they rigorously quantified the uncertainties in the flame model, and then they did the forward propagation of these uncertainties to the growth rate prediction, and they obtained this a PDF of for the growth rate. But one thing which was inherently assumed is that the flame model, which was obtained from the LES-SI approach, was obtained with all the known boundary conditions, which is not the case. But so that means they didn't assume any epistemic uncertainties coming into this flame model determination or estimation. So in another case, Abdonin studied the effect of the uncertain flow conditions and the boundary conditions on the response of a laminar flame, of a Corny law flame, and then he was able to quantify the uncertainties in the flame response, the FTF here, because of the uncertain boundary conditions. But one thing which was missing from this study was that since the system identification was applied on a laminar flame, the uncertainties coming from the noise was absent, and then that's why basically the uncertainty from the SI was negligible. So there was no aleatoric uncertainties per se. So they only had epistemic uncertainty. So this brings us to the current objective. That is that, so how do we take into account the uncertainties in the flame model when you have both epistemic uncertainties, which are coming from your uncertain boundary conditions, and also from the uncertainty coming from your applying the SI on data corrupted by noise. So how do we do that is the basic question which we are going to solve. So in order to solve this, we will be looking at a system which has a turbulent flame, and then also has an uncertain boundary condition in terms of the combustor backplate temperature. So so anytime we talk about uncertainty quantification, then we always think about Monte Carlo simulations. So that means we draw a huge number of samples on the uncertain variable here, that is the combustor backplate temperature, and then we can do an LES-SI for each of those, and then determine the statistics of your flame model. But this in the setting for an LES is computationally prohibitive. So we need to come up with some better solutions. So people have worked on this, and then they show that surrogate can be a better a substitute to doing this kind of analysis, where the surrogate model trains on the responses from your LES, and then which is more computationally cheap. And then with this, you can on this cheaper surrogate model, then you can perform the Monte Carlo simulation. So basically, it's very easy to train your surrogate model, where you only require, say, of the order of 10 samples to get your surrogate model, and then we can apply. It's a very cheaper process to then apply the Monte Carlo on this cheap surrogate model. So now we know that we can use surrogate model, but this poses a challenge, as I said earlier, because in the term, when you have both epistemic and aleatoric uncertainties. So basically, in terms of research question, or the question what we can try to solve is it poses two different challenges. So that one being the high output dimensionality of the surrogate model. That is, we are trying to learn the FIR, so which has 30 to 50 coefficients when in general. And then this is a very high output dimensional system. And then second one being these FIR coefficients are not unique, because as I said, we are applying system identification on data corrupted by noise. So how do we account for this remains a challenge. So here we propose an univariate Gaussian process, which will try to counter the two challenges which we have. So first, what we do is we conceive our surrogate model, or basically the Gaussian process which we choose here, to be a function of only the time delay and the temperature. So every FR coefficient, then we assume here, is a function of time delay and temperature. So this negates the fact that we are now having a high dimensional output system. So then how do we employ this kind of Gaussian process to solve the problem? So here I'm just going to go about the training procedure. So let's say we have 10 or of the order 10 simulations. Then these simulations are done on different temperatures, which are drawn uniformly from the investigated temperature range which we want to look at. And then we perform the LES, and then perform the system identification on these temperatures. And then we have this kind of a training matrix, which shows basically the means of the FIR coefficients for different temperatures, which is tagged here. And then we use this training matrix, and then we try to fit a GP hypersurface. So this we do it as a function of the time delay for each coefficient and the time and the temperature. And then this is the nominal GP hypersurface, which we get after the training. Yes, so once we have this GP hypersurface, then how do we account for the uncertainties from the system identification and also the GP model approximation, and also the epistemic uncertainty of the different temperatures? So for this, we propose the bootstrapping methodology, so which is explained here. So along with the system, when we do the system identification for each temperature, we are also supplied with the information of the covariance of the FIR coefficients, which are estimated. So once we have these for all the temperatures, then we draw, like say, P realization. So P being 500 in our case. So we'd say we draw 500 realizations within these covariances of the system identifications. So thereby we capture the uncertainty coming from the system identification. So once we have the like say P realization or 500 realizations, then what we do is we draw say S samples. So S being 10,000 or 1,000 here, just for the case, we draw 1,000 temperature points, which are in the minimum and the maximum of the investigated temperature range via Latin hypercube sampling. And then for each prediction temperature, what we do is for each prediction site, we recalculate the GP model for the each realization which we had earlier from the system identification covariances. So for each realization, then we do the prediction at S temperature, or the test temperature which we want to do. And then once we have the prediction, then we draw the Q realizations. So Q again being here again 500. So these realizations take into account the model approximation. So these Q realizations are drawn from the covariance of the GP model approximations. So this means by doing this way, we also take into account the uncertainty from the GP model approximation. So once we have this, then we do then we aggregate all the ensemble uncertainty estimates for each prediction temperature, and then we aggregate all these ensemble of uncertainties, which will give us the total prediction uncertainty at the prediction site. So this total prediction uncertainty, what I'm talking about, has the uncertainty from the epistemic, that is the different temperatures, and also from the SI, and also from the model approximation, which is aleatoric. So as Ushni said that now we have the hammer ready, then we need a nail to pin this upon. So in this case, we use our thermoacoustic setup, which is the noise din compressor. As I said earlier, this is a premixed flame, a turbulent premixed flame, which has been experimentally studied at EM2C, and then this setup was numerically validated and was also also the dynamics of this was studied by our previous colleague at the chair, Malte Merck. And the only difference from here, this setup, when we do the simulations where the change of the acoustic boundary conditions, that we use the classical NAC-BC, whereas Malte used the refined CBS-BC, which also ensures reflectiveness at all the frequencies. So one thing which has to be noted in this is that when the simulations were done, the backplate temperature here, which was not measured, was only tuned to a certain value, say 823 Kelvin in this case, so that the flame shape which was obtained from the simulation was in good agreement with the experimental observations. So therefore, the backplate temperature can be ascertained as an uncertain parameter in this case. So yeah, then after having assumed this backplate temperature, then we perform an LES on that, assuming that temperature. And then here I show the FTF and the flame impulse response at that temperature. And as you can see, the phase is well predicted compared to the experiments. So the cyan color shows the experiments, and the blue color shows the LES SI results, and the shaded region shows the certainty of this prediction. And as you can see, the gain is not so much well predicted. This may be because of the inadequate description of the flame dynamics, or maybe also because of the uncertainty of the combustor backplate temperature, which we have assumed. So now it would be interesting to see that since we are doing the ramp on the temperature, say from 700 kelvins to 926 kelvins, which we are trying to look at. So the base case is 823. And then we see how does the flame shape looks like when we do these ramp in the temperature space. And then here I've shown the extremes and the mean. So at 700 kelvins, you see that the flame is more longer compared to the flame at 926. So this is because of the cooler backplate temperature here, so which will then not aid the flame base with, here there's a higher heat loss, so that means you are not supplying the flame base with the radicals which are at adiabatic flame temperature, and thereby the flame tends to be the flame tends to be more longer. Whereas on the other hand, here the heat loss is much smaller because of the higher temperature, and then you are supplying the flame base with more hotter combustion products, and then that's why the flame speed is much more higher compared to this, and then we have a shorter flame length. And we can also see a slight reattachment of the flame to the outer recirculation or the rim of the injector here. And these are the normalized heat release rate, which is shown here and which has been accumulated over 70 milliseconds worth of LES data. And once we have obtained these, then we look at the flame transfer functions for these three temperatures here, and we see that because of the change in the flame length, we see the FTF delay is also either more gentle in the slope and more steeper in the slope, as was also shown in the earlier previous studies, like from Mejia and Duchesne. So once we know how does our flame look like, and one thing I have to say here is that although the flame has changed the shape, fortunately the flame response is more smooth, and that is good results for us to apply our surrogate model. Otherwise, if there is any discontinuity in the flame response, like the flame response, then you would need a slightly different strategy to apply your surrogate modeling. So here I show you the results from our GP. So the GP results are shown in the black line, and the uncertainty from that is given in the black dashed line. And the blue line shows the cyan color shows you the experiments, and the blue line shows you the LES results. So here you can see that the GP is, let's say if we look at 823 Kelvin, the GP here, the GP interpolation here shows, so here while training, we drop the 823 kelvins from the training, and then we use all the other training temperature points for training, and then we predict it at 823 kelvins. And then we see that the GP interpolation is better compared to the LES. And that means the GP is able to learn the response surface accurately. So once we have done that, as I showed earlier about how do we determine the total prediction uncertainty, that we do now. And I show here the total prediction uncertainty on the whole investigated temperature range. As you can see, the confidence intervals are much higher compared to here in this case, because here we are predicting at a known temperature. So that means we don't have the aleatory the epistemic uncertainty yet. So once we include that, we have a very higher confidence interval. It can also be shown from these from the left plot, which describes the PDF of a single FIR coefficient when you do the prediction. So here these three dashed lines shows the aleatoric uncertainties. That means when you are trying to predict at different known temperatures, that means there is no epistemic uncertainty, and then you have this and then predict and do the PDF of these prediction, and then we see that these PDFs are much smaller, and then we, as I said, we aggregate all the uncertainties, these aleatoric uncertainties, and then it results in a very wider PDF, so which results in a very wide confidence interval here. So thereby, this method shows that we can successfully account for epistemic and aleatoric uncertainties with this kind of a surrogate modeling technique. So finally, what we can also do is once we have our surrogate model trained, we could then infer on another boundary condition within the or we could interpolate it at different temperature here. And when we try to do that, let's say at 850 kelvins, this is the plot of FTF and FIR 850 kelvins, where the LES data was available but was not used in the training. And you can see that the gain and the phase are in much better agreement with the experiments at 850 kelvins. So this shows that, and also the FIR, that it's in better agreement with the experiments. Not better, but it's much better than what was assumed with 823 kelvins. So thereby, the Gaussian process or the surrogate model can be also used to infer the unknown thermal boundary conditions. This brings us to the conclusion of the work. One thing is, so first thing is we can build a surrogate model on the with the help of LES SI, and then we can build a GP hypersurface, and then that could be used in predicting the total prediction uncertainties, which results in a wider, we have seen a wider confidence interval. And then lastly, the GP model can be leveraged to infer the unknown thermal boundary conditions in the temperature space, which we have included. So one takeaway from this is we are done for, say, a premixed flame. So this can also be applied to a spray flame which has uncertain, say, spray boundary conditions such as the droplet size, velocity, etc. And then we can look at how the uncertainty of that results in the flame impulse, flame model estimation in the case of spray flames. So lastly, I'm recently have touched up with Michael McCartney, and then we are in touch with the GE, whether they could provide us with some amount of spray data where we could apply the current shown uncertainty quantification method on their experiment on their CFD data. The talks are still ongoing, and we also have some insights that we could also apply the Bayesian neural network, which Michael is working upon, and maybe he will have something to say tomorrow. And then we are also in touch with Hermano and Davide at Surfax. So Hermano being the analyst at ESR regarding the LES of the Sika spray flame dynamics. And then this is research in progress. Yeah, thank you. And I'll be happy to have any questions.